Lewis bases are defined as electron pair donors. By contrast, Bronsted-Lowry bases are defined as proton acceptors. Looking at a variety of different bases from their Lewis structures, we see that ammonia, which we see here, NH3, water, H2O, and chloride, Cl-, all three of these bases have one or more pairs of electrons that they can donate. Okay. By the same token, however, since they have a pair of electrons that they can donate, they also can accept an H plus ion to form their conjugate acids. And so we see that in both these cases, for Lewis bases and Bronsted-Lowry bases, they all have a pair of electrons that they can donate, which we see here. And so therefore we can say that Lewis bases are always Bronsted-Lowry bases, and vice versa, Bronsted-Lowry bases are always Lewis bases. Next, we'll look at Lewis acids, which are defined as electron pair acceptors. This contrasts with the definition for Bronsted-Lowry acids, which are classified as proton donors. We can see here that in order to be an electron pair acceptor, a molecular ion has to have an empty orbital to which the electrons can be accepted. Okay? This comprises a large number of different types of molecules. Essentially, anything can be a Lewis acid. By contrast, for Bronsted-Lowry acids, Bronsted-Lowry acids, because they have to be proton donors, they have to have a hydrogen, an ionizable hydrogen, in its chemical formula. And this is limited to only a few types of molecules. Examples we have here are molecules such as HCl, hydrochloric acid, and HNO3, or nitric acid. And so we can say that Lewis acids are not always Bronsted-Lowry acids. Right? Examples of Lewis acids are electron-deficient species, such as boron, beryllium, and aluminum compounds. So here we have an example of boron trichloride, which can accept a pair of electrons. Also, metal cations such as copper 2+ and lithium 1+ are also Lewis acids because they can accept a pair of electrons as well. Okay? And finally, molecules with multiple covalent bonds are also defined as electron pair acceptors.
To summarize, Arrhenius acids are defined as substances that produce H+, and Arrhenius bases are defined as substances that produce hydroxide directly. More general definition is the Bronsted-Lowry concept of acids and bases, where Bronsted-Lowry acids are defined as proton donors and Bronsted-Lowry bases are defined as proton acceptors. You can see from this definition that everything that is an Arrhenius acid is also automatically a Bronsted-Lowry acid, and everything that's an Arrhenius base is also automatically a Bronsted-Lowry base. However, the Bronsted-Lowry definition also includes some substances that are not included in the Arrhenius definition, and that's why the circle is bigger. The most general definition of acids and bases is Lewis theory, where Lewis acids are defined as electron pair acceptors, and Lewis bases are defined as electron pair donors. Now, it's important to remember that everything that's an Arrhenius base is automatically also a Bronsted-Lowry base, and everything that's a Bronsted-Lowry base is also automatically a Lewis base, which is why the circles get larger as we move from Arrhenius to Bronsted-Lowry to Lewis. It's also important to remember that, in principle, since all molecules have empty orbitals, therefore everything can accept a pair of electrons, and therefore basically everything is in theory a Lewis acid.
In this example, we are asked to classify each of the species in the reaction shown below as either Lewis acids or Lewis bases. In the first reaction, we have the reaction between the oxonium ion and hydroxide to produce water. Now, in order to classify these species, it's important to remember the definitions for Lewis acids and Lewis bases. Lewis bases are defined as electron pair donors, while Lewis acids are defined as electron pair acceptors. So in order to determine whether oxonium and hydroxide are Lewis acids and bases, it's easiest to first write the Lewis structures. So here we have the Lewis structure for the oxonium ion, and here we have the Lewis structure for the hydroxide ion. We can see from the reaction that the 2 electrons from the oxygen on the hydroxide ion will be donated to the hydrogen atom on the oxonium ion. In this process, the electrons from the oxygen-hydrogen bond will move on to the oxygen to produce 2 molecules of water. So from this reaction mechanism, we see that hydroxide is donating a pair of electrons, and therefore hydroxide is Lewis base, whereas the oxonium ion is accepting a pair of electrons from the hydroxide, and therefore the oxonium ion is a Lewis acid. Moving to our next example, where we have the reaction between BF3 and ammonia to produce the adduct BF3NH3. We first write the Lewis structures for each of the species in this reaction, and we see again that in the case of ammonia, 2 electrons from ammonia are donated to boron on BF3. And therefore, in this case, ammonia is acting as a Lewis base, and since the boron is accepting a pair of electrons, BF3 is acting as a Lewis acid.